So this talk will be about simulating time-gated cameras efficiently. But first, let's start with some background on what a time-gated camera is. So take this photo of a Coke bottle. A normal RGB camera will sum up all the light that lands at each pixel, but it keeps no record of when that light arrived. And here's the same bottle, but filmed fast enough to see light itself move. So a single pulse enters from the left and sweeps through over time. And if you freeze one instant, you've isolated the light that arrived in one narrow slice of time. And this is exactly what a time-gated camera captures. It opens for a brief window and keeps only the photons that land inside it. So why would this be useful? Well, if we look at this foggy image on the left, you can't really see what's down the road. But through a gated camera, the car is clear, and we even see these people hidden on the right that you couldn't see before. It's because the gate keeps only the light that came almost straight back from the car, and everything that's scattered in the fog arrives at the wrong time and is rejected. And this same principle powers a lot of other cool applications, such as non-light-of-sight imaging and proximity detection. So these are real cameras, but why would we want to render them? So methods like gated to depth turn a few gated slices into dense depth, but training needs gated images paired with ground truth depth, which can be difficult to capture at scale. So physically accurate rendering can instead hand these methods correct ground truth labeled data, but it's only useful if it's accurate and fast. So before we dive into time-gated rendering, I'd like to note that there's been a lot of work in time-of-flight rendering. And on the left here, we have these transient animations simulating full time-resolved response of light throughout a scene. And you can see it propagating. And this has been studied for surfaces and in participating media. Time-gated rendering is a specific slice of this transient. So instead of the full response, we keep only the light in a narrow time window, which makes things a bit harder, as we'll see. So now let's formulate the problem. So steady-state rendering effectively assumes light travels infinitely fast. Each pixel integrates the contribution of all transport paths, regardless of how long the light spent traveling. Time-gated rendering changes one thing. We insert a weight W on each path's travel time, and the total duration, which is the total duration that light spends along the path. And for a gated sensor, it's usually a box with the value of 1 inside the gate and 0 outside. So a path contributes only if its travel time lands in this interval. And note that if we trace naively, narrow gates can make it hard to sample a path of the right length. So why is this hard to sample? If you look at bidirectional methods where we trace a sensor subpath and a light subpath with no knowledge of the time gate, once both of these subpaths are fixed, connecting them leaves no sampling decision. So the connection distance and therefore the total duration of the path is whatever it happens to be. That kind of sucks. Episodal path connections restores a degree of freedom by inserting one extra bounce at a point chosen to hit a target travel time. And the set of all such points results in, an ellipse in 2D, but an ellipsoid in 3D space, where the two endpoints of your subpath are the foci. But this ellipsoidal vertex must also lie on actual scene geometry, so you can actually form a valid path. So every connection requires intersecting this ellipsoid with the scene geometry. So the cost of time gating is bolted directly to scene complexity. So for simple scenes, like for this deformed bunny with 23 triangles, EPC works quite well, but this geometric query has a cost. And when we go to scenes with like 200,000 triangles, we see that it takes around 16 minutes for one SPP. And this performs worse than BDPT does in 30 seconds. So our goal is to keep the ability to target specific path lengths or travel times, but decouple the cost of time gating from scene complexity. So for the rest of the talk, we'll be showing how we get there. So our contribution comes in two parts. First, we show a new way to formulate the problem. We show that all time-valid connections for a given point form a single geometric region in space-time and effectively turn the whole problem into a search. And second, we make that search efficient through an acceleration structure that finds time-valid connections with a cost that doesn't depend on scene complexity. So let's build the core idea from light itself. So we look at this emitter in the middle in 2D space, and we fire a pulse. And for convenience, we set the speed of light to 1, so light covers 1 unit of distance per unit of time. And we see that light propagates out in a wavefront in this kind of circle that grows at exactly at the speed of light. Now if we add a time axis with the pulse at time 0, and then place each wavefront circle at the time it occurs, we see that this sweeps out a cone. And this is everywhere the emitter's light can reach in space-time. And this is the emitter's light cone, which opens kind of upward in time. Now to connect this to path tracing, let's drop to one spatial dimension plus time so we can draw everything a bit more cleanly. So in one spatial dimension, this cone becomes a chevron, or this V shape. And because light moves at speed 1, every path segment is at a 45-degree line, where rise equals run. And in 1D space, we can only really go left or right. And a light subpath from the emitter is a chain of these legs climbing in time. And we can store each of these vertices at its position and accumulated travel time. And travel time here is just the vertex's height on this plot. And we can trace from the camera the same way. Here we draw sensor vertices downward to kind of keep them visually separate from the light vertices, though their accumulated travel time is still positive. So now we trace paths from both ends. So the question is, which stored light vertices can connect to a sensor vertex and result in a path that's inside of the time gate? So if we store all these light vertices, and we fix one shade point, and start with this single target length, this tau star, connecting a vertex v to q as one segment to the path, and the resulting path length is a vertex's accumulated time plus the connection distance plus the shade point's travel time. This connection is valid only if this sum matches the target time. But note that since we fixed the shade point here and want to query with it, this q tau is constant. This means that the light side, so extending the light subpath, must result in arriving at the shade point's position, so along the vertical axis, at exactly this target time after the pulse. And this is essentially a deadline. And since joining the two subpaths means tracing one connection segment, the question then becomes, which of our stored light vertices can reach the shade point's position by this deadline with a single segment? So let's try connecting some light vertices to the shade vertex. We see here that light vertices that are too far or too close in space-time miss the deadline. And if we look at the ones that actually hit it, we see that they must lie on these two 45-degree line segments with the deadline at its apex. And if you look at all such light vertices, it traces out our chevron again, or this V shape. So in 2D space, you can think of spinning this chevron around so we get back our cone. And notice that in this case, or both of these cases, this surface has 0 thickness. So the probability of us sampling a path of this exact time is 0. Therefore, we need to generate 1, which is exactly what ellipsoidal path connections does. So recall that EPC first samples the target travel time and then finds another vertex such that the resulting path is time valid. So given a camera and light subpath, these blue and yellow dots, we can think of it as extending the light subpath by one segment, which results in this upward light cone. And the intersection of these two light cones gives an ellipse in 2D, and this becomes our ellipsoid in 3D, and we have a derivation for this in the paper. But remember that EPC also needs to intersect this ellipsoid with scene geometry to find a valid vertex in the scene, which is where its cost comes from. Now, this is for the case where the time gate is a delta, but luckily in practice, this isn't true. So usually we have a min and a max time for our time gate, and every range, or every time inside this range is valid. So this maximum gives us an outer cone, and the min gives us an inner cone. And any time in the band between them is valid. So now we have a cone with thickness, and we call this a light cone shell. So instead of a surface, we now have a volume, so our stored vertices can actually fall inside. And you can think of naive methods like a BDBT as rejection sampling this shell. So EPC guarantees a gate by construction, but instead we can pre-trace light subpaths and check if they are time valid. And this validity test is actually pretty cheap. For shell membership, we just have this one inequality where every term here is stored or is trivial to compute and doesn't require us looking at any geometry. So the whole problem now becomes a search. Among potentially hundreds of thousands of stored vertices, we want to find an important sample of the ones in the shell given a query shade point. And making that search fast is our second contribution. So to avoid scanning all of them, we organize them into a balanced binary tree over position and accumulated travel time, and sample through stochastic descent. At each node, we pick a child in proportion to an upper bound on its contribution, and one route to leaf walk selects one vertex with a known probability. And this is stochastic light cuts, which brings the O of n scan down to O of log n. But these bounds only know position, power, material, but nothing about the actual time gate. So as is, we would steer samples towards close and bright vertices, irrespective of if they could ever land in the gate. So we fold the shell into the traversal. And we saw it before, we have a test for a single vertex, but now we have a hierarchy of nodes, and nodes stand in for thousands of vertices. So we can ask for a subtree's bounding blocks how much of it overlaps the shell. If there's no overlap, then no descendant can land in the gate, so we can prune that subtree without ever looking inside. If there's some partial overlap, we can scale the node's power by the estimated overlap, so we can steer traversal towards where the time-valid vertices actually live. And pruning is just an extreme case where there's zero overlap and just zero power. So computing the exact overlap geometrically is difficult, but we can easily get an approximate bound by comparing the spatial extent of the node and the distance to the query point. So emitter vertices, for example, sit on the floor at time 0, so they only vary in space. So here the shell is a cross-section, and the valid connection distances are one interval. Here we have the light cone shell in green, and we can intersect that with the distance range from the query point to the node to get the spatial overlap. Everyone else varies in both position and time, and thus the cross-section of the light cone shifts as time changes, so we can't just use one interval. So for these vertices, we slice each node's time range into power buckets and keep the buckets whose slab touch the shell and sum their power. And we see here for this purple bounding box over here that these buckets can make a kill that pruning can't, as a node can pass the box test with all its power in invalid slabs. So nothing so far was algorithm specific, and we can drop this into anything that makes connections between subpaths. We should choose to do it in BDPT, where we first trace light subpaths, store all these vertices, build our acceleration structure, and now every connection becomes a shell query. And we use standard BDPT MIS weights to suppress geometry term singularities. And you can kind of view this as BDPT with probabilistic connections, just specialized subordinate sampling time-valid connections. And I'll go into some results. So we first test on some, I guess, more complex scenes, starting with this feature jar with 383,000 triangles, a gate width of 2% of the scene size, where the emitter is a collimated beam shooting at the back wall. We see it takes quite long for ellipsoidal connections at 1 SPP. So we compare with BDPT at 30 seconds, and here's ours. And we achieve 5.5 times lower relative MSE at equal time on this scene. Now this one with 1.5 million triangles, you see it takes almost 2 hours for 1 SPP with EPC. So we compare with BDPT at 30 seconds. Here's ours. We have around 4.5 times lower relative MSE. And then we also perform some ablations. Here we show sweeping the gate width. And note that when the gate is really small, EPC is better than our method. It's because it's the only method that can actually sample past an exact length. So as the gate approaches a delta, as no other method can really match EPC. But in practice, gates are never that narrow, so it's okay. So now let's go into some applications. So if you remember the foggy tunnel scene that we opened up with, we now recreate that scenario in simulation, as our method is also directly applicable to volumetric rendering. So first we have the steady state image where the far car is kind of lost in the haze. Here's a transient animation showing how light would propagate throughout the scene. And here we have like a camera and the emitter almost co-located. So if we gate at certain depths, we can first target the near car, and we can also do the same for the far car, and it's pretty clear. And at equal time, the error of our method is lower than BDPT. We show one more application for proximity detection, where we have a car traveling through this city with a lot of triangles, and as it approaches the intersection, we want to get a time gate and see how far we are away. And here we see that our method is able to clearly render like the stop sign, the car, and the ground also. So to wrap up, we showed that time-gated rendering has a geometric core. The constraint that coupled the whole path collapses to a single point in space-time, reducing the problem to a search. And we made that search fast with a traversal driven by shell overlap. And now it scales in the number of stored light vertices, but doesn't touch any scene geometry. And now for some future work and limitations. So one direction could be for time-gated caustic rendering. So currently, we emit the BDPT strategies with no controllable connection point, such as light tracing or light tracing with NEE, which are important for caustic rendering. So potentially merging with density estimation methods, such as VCM or UPS, could help us render these efficiently in a time-gated setting. Another would be exploring resampling where MIS weights that fold our traversal probability into the weighting. As currently, we kind of disregard that and just use standard BDPT MIS weights. This has been looked at in the steady state setting, but seeing if it helps in time-gated rendering, where perhaps maybe the main cause of variance is the time gate, would be an interesting direction. So thank you for listening, and let me know if you have any questions.
Thank you for talk. to your comparison result, that car with a red sign. Can you go back to that slides?
Yeah.
I see that your result is much less. Yes, this one. You have much less you have a convergence much better, much less noises. But you can see the sign you are much blurred than the PD-PT. Why?
The stop sign is more blurry.
Yes.
I think that might just be the texture, and then the BDPT is a bit noisy, so some fireflies making it maybe look shinier.
Oh, you mean that's maybe the artifacts?
Oh, you mean for our method?
Yeah.
Yeah, so there are artifacts when there aren't enough light vertices stored, but here I think I used enough. I guess it looks kind of faded. I don't really see it.
Do you have a ground truth or?
Well, I do, not in the slides.
Okay.
Yeah.
Oh yeah. Thanks.
Yeah.
A super interesting presentation. So, disclaimer, my hobby in life is doing relativistic simulation with transient rendering. I tried and it's fun, but it's very noisy. From what I saw in your method, nothing will prohibit you to have Lorentz boost in relativity. What's the name again? In just the normal regular relativity. I wonder if you tried to have a Lorentz boost at some point to fake a camera that goes near the speed of light. Maybe it could have application in astrophysics, visualization, and stuff like that. But yeah, I just wonder.
Okay, yeah.
Thanks for your presentation. It's a very interesting topic, I think. Could you, I think I just missaw it, but could you please go back to the bedroom example, slide 43, I think?
43.
And show the difference between yours and bidirectional path tracing.
Yeah.
Yes, I missaw it. Never mind me.
Oh, okay.
Thank you very much.
Yeah.
Hello. Yes. Thank you for the talk. These are usually very useful if the speed of light is very slow, which it isn't, but the speed of sound is quite slow. I've explored thought applications for acoustics because it could be quite relevant there to accelerate render in that case.
Yeah, I saw there was some work on acoustics rendering, though I haven't looked into it in depth, but I think, they could share some similarities, so it'd be interesting to look if we can apply some of the methods from here or previous works to acoustic rendering.
Thank you.
Yeah.
Very nice presentation.
Thank you.
I was wondering, how is, for real applications, how is the time gate chosen? Because you don't know a priori how far something is.
Yeah.
So, yeah.
Yeah, so usually in real applications, I guess you'd pick a distance or a time for your time gate, because I guess you know the speed of light. So when you open your gate, the time that light will take is from you usually have a camera and then emitter, a pulse laser kind of synchronized with your shutter. So you'd pulse, open, or you'd pulse, maybe wait a little bit, open, and then it would come back, bounce off whatever you want. And then you'd have your time-gated image. So from there, you know how far, or at what distance you'll be actually seeing. It would just be the speed of light, I guess divided by 2.
Thank you. Yeah, that makes sense.
Something like that, yeah.
Okay. Let's thank Jack one more time.